Let's begin. So we're still kind of talking about just practical issues with MCMC. So I want to show you one more thing, is how to tune this, the step size, and what to look for. You can make this more technical if you want. So there's all these different statistics. The Gelman-Rubin statistic is the popular one. I'll tell you what it is, and I'll tell you what the issue is, the part that you would have to work out the theory, but it's always being updated and corrected. It's not quite a real, it's not exactly the right diagnosis. You'll hear Gelman walk around and say this is surefire, you can't defeat this, there's nothing else there. And you're supposed to say, of course you can, you're being ridiculous. And he'll end up saying you're the smartest one for calling me out on that. He's a high-powered guy, but he likes to pull everybody's leg. And so he entertains himself. To know the type. Okay, let's come back around to this. So we've been running this thing and we have different starting values. Let's just collect some more data, see how this thing works. So collect some more data. We've got the same true mu, true sigma. Let's reduce the data set size. The reason we crank that up so big is just to show that numerical instability can kind of creep in as you're computing that likelihood function. So if you're computing it in the form of a product and the product expands with n, you're going to see more and more numerical problems as n increases. Also, I'll kind of point out, in terms of your proposals, things can kind of deteriorate as n gets bigger as well. So if you use the independent proposal, so if you use something like gamma for proposing the precision parameter, you would have to know about how wide that gamma was. There's two parameters in there. You might adjust it to the mean where you're previously located, but your variance is going to be growing and shrinking depending on how you do that at every step. So that's not super desirable. If you picked a static gamma, you kind of need to know where the mass was of the distribution. If you kind of knew where it was, you could do something like that. But as you ended up increasing n, the variability of the process is going to be, or the variability in mu is going to be decreasing, but also the variability in phi itself, and so that would be getting squashed down. And so if you used a static proposal and your problem changed, you probably need to change your proposal, and that's kind of defeats the purpose of what we're doing. So we want proposals that are flexible and they can adapt to any problem. So again, this should pique your interest that for all kinds of different processes, how would you come up with proposals? That's the entire field of MCMC, is answering that question. So we're kind of giving you the basics for simple models that are unimodal, that only have one mode. And you could kind of use this normal random walk, and then you're just tuning the variability in there. So the process that we're looking at in this example. So got more data. So 31 data points. There's nothing special about that number. And we'll run this thing again. We'll see how it runs. This is going to have our old starting locations. So it started way up here, boom, and it came down. And it looks like it kind of converged in some sense, but there aren't enough samples right here. So I can kind of look at what I've done. I have the burn-in period cranked way up, so I didn't have very many samples at the end of the day after I burned in. So if I remember correctly, last time we had to crank up the burn-in period really high to get it to converge. So I think with this example, we don't need to do that quite as much. We can bring this back to maybe 10,000 samples, and our burn-in period is maybe 1,000 or something like that. We're going to have some initial starting points as well. What I'd like to do is bring this a little bit closer in terms of its initialization to the truth. And so we've talked about burn-in pretty extensively, but now I'd like to talk about just tuning it once it's actually hit the target distribution. So once it hits the target distribution, the terminology we use is the Markov chain is stationary. So it's going to hit that distribution and it's going to stay within that distribution. During the burn-in period, it's walking through that same process, but it hasn't converged yet. So once you're in that distribution and you stay inside of that distribution, that's called stationary. So just in terms of tuning this thing, I've got this step size over here. I made it really big last time. Let's put it back to 1 and kind of, well, actually, let's keep it as big. And I brought everything close to the truth. So my true mu is still 7. I picked it to be, my initializer to be 1, so it's kind of in the ballpark. It's a little off, so there is a little bit of burn-in in there. So to combat this, maybe I'll let my burn-in be 100. Okay, so it'll walk over to that distribution pretty quickly. And phi has kind of a reasonable starting location. Our true phi is 1/4. In this example, I picked it to be 2. That's a lot closer than like 20. So I don't want to completely cheat and start it stationary, because you never really do that in practice. So let's run this thing again. So as we can see, here's our chain that we just picked. So I just ran this thing. Here are all my samples from my chain. Here's my burn-in period. It's come down. The red dot is right there, if you can see it. And it's kind of walked around this distribution. And if I look at my one-dimensional trace plot, this is the one from mu, it looks like that. And so it's sticking a lot. Can anybody tell me what's happening in this example? I think it's coded up correctly. So what's happening?
It's never accepting the jump. If it's stuck, it's very really surprising.
Right, we kind of know that the distribution somewhere around here, we can see some semblance of convergence, that it's gotten down here and it's stayed there, but the proposal is bouncing it way over here, or way out here, and it's staying at the previous location. It's saying, you just proposed this thing that's shooting me way outside of the stationary range. And so it's sticky. We don't like that. So it plateaus a lot. You'll notice that this chain is highly autocorrelated. And so that's a good way to check convergence. So MCMC chains shouldn't be highly autocorrelated with each other if you want to use those samples in an IID fashion. Now you could run this chain much longer. We could collect a lot of samples from it, and then I could thin them out if I wanted to, or I could shuffle them or something like that. You're still going to have the same point showing up over and over and over again. And so you wouldn't want to say you've converged until you've kind of really explored that space really well. So you'd have to run it a long time to do that, and probably you could thin your chain. So that you're going to combat that with a lot of computation. So these samples are very autocorrelated when it's sticking. So let me just write that down for you. So chains that look like this. So these are called trace plots. And so this is a 2-dimensional trace plot. Most people don't look at those because they can't really see what's happening exactly. But they'll look at these 1-dimensional trace plots. And that one's sticking a lot. It's stuck at the same place. So that chain is highly correlated with itself. And if I look at this chain for phi, same thing's happening. So we already know what the right answer is. So in general, you don't know. And so but you have to be commonsensical about it. If somebody showed you this and they showed you a chain like this, you'd say that's probably not converged. I think everybody could spot that. So sticking looks like this. And everybody agrees on this term. So the samples are autocorrelated. Highly autocorrelated. And that's bad. We don't like that. So again, one thing you could do from an engineering perspective is run the heck out of the chain and then thin it.
May I ask a very novice question?
Please.
How do you know, or what exactly What shows that those samples are autocorrelated?
This sample right here is the same sample for a long time. So autocorrelation, a one-step autocorrelation, if I ended up looking at, let's say I have a whole bunch of samples in here. And they stick right there or something like that. So what I'm going to look at for my one-point autocorrelation is I'd look at 2 points in sequence. So these are one time step apart from each other. One is the operative word. And I'd end up doing that for every 2-point pairs. So I'd look at this point and see how correlated it is with that. This point, how correlated it is with that. This point, how correlated it is with that point right there. And I could come up with these pairs. So that point and its 1-point successor. I'd do that all the way through the chain and I'd look at its correlation. Okay, so I could plot its correlation. So this is going to be 1 time point lag. So that's the lag step right here. And maybe the autocorrelation, it's going to be a number between 0 and 1. Maybe it's high. So right here, where they're stuck, there are the same points over and over and over again. So it has a high 1 time point lag autocorrelation. Then I could end up looking at my 2 time point correlations, my 2 lag. So I would jump 2 points. I'd grab that point. I'd do the same thing here. I'd grab those and create 2 columns out of everything. There'd be slightly less data in there because there'd be slightly less 2-point correlated values. And I would plot that autocorrelation. And it would be coming down a little bit. And I could do this for 3 lags, 4 lags, 5 lags. And I could look at this autocorrelation plot. And it would start dying down. What you might do is say there's some threshold in here for how autocorrelated you wanted everything to be. So it's kind of just a common sense sort of diagnostic. So I do look at autocorrelations. I look at how autocorrelated my chains are. But again, that's not the whole story because I could shuffle everything. And that's not going to correct everything. It would take out the autocorrelation, but I still will only have sampled a few points in that posterior density. So how do you tell that things are autocorrelated? At the 1 lag step, they're very similar to what they were previously. So something like this, it's sticking on kind of the same point for a long time, so it's highly autocorrelated. It jumps, kind of brings down that correlation a little bit. So maybe at these big time steps, right here, maybe that's 10 time steps, then the autocorrelation falls down. Does that make sense? So some of these terms that I use, I kind of expect maybe you've heard them before, but if not, I'm happy to tell you what they mean. So we could do the other phenomena. So if it's too autocorrelated because I'm making my proposal variances too big, I could go the other way and shrink them. And all the adaptive samplers out there, they do exactly what I'm doing. They just have some automated control over it. So they maybe look at the autocorrelation and decide whether or not you need to bump up the tuning parameter or you need to bump it down a little bit. So let's go the other way. My step was huge. It was 100. So let's go the other way and make it really small. Smaller. We'll rerun this thing. There's my thing. It hasn't even converged yet. So let's at least bring everything a little bit closer. So if you saw this plot right here, you can see that I haven't even converged. It's still moving. It's actually just tippy-toeing. Can you tell that this is highly autocorrelated as well? So that's also highly autocorrelated because the point that we accept at the next step is very similar to the old point. It's not exactly the same point, but it's very similar to it. So it's also very autocorrelated. We haven't even burned this chain in long enough. So chains with big proposal variances will reach stationarity quicker, but then you'll be jumping outside of the target distribution a lot. And you can identify that by sticking. Through sticking. Let's at least bring everything a little bit closer. I'm going to make this 0.4 so it's closer to the truth and we can combat the burn-in exercise. And mu in it I'll make that a little closer to the truth as well. So let's run it again. I can come back and look at my other trace plots. We'll do that once we rerun it. Everything's rerun, and it looks like this. So has this chain converged? Well, it's certainly like now going up and down a little bit. So it's a little bit closer. It looks like this has come down. Remember our target, this 0.25 is over here. And so it looks like it's gotten down there. And it's probably in the posterior mass, tippy-toeing around. So this doesn't look converged. Again, what you can do is you can crank up the number of iterations. So let's do that. Let's actually start it right at the truth so that we don't have any burn-in period to deal with. Very unlikely that there's a burn-in period. Every once in a while it might be shifted from the truth with low sample sizes. So let's rerun this, and I'm going to run it for more iterations. I've started it at about the truth, so I bet my burn-in's pretty good. I'll even crank it up. Maybe that'll make me feel better. I've done more computations, so maybe this will work. And so if I'm thinking about the acceptance ratio, and I'm thinking that the acceptance ratio should be high, just moving very slightly from what we've just accepted seems like a good idea, and that will crank up your acceptance ratio. So versus the other thing in sticking, where your acceptance ratio is exceedingly low. So we stay at the same point because the acceptance ratio is tiny. So this does the opposite thing. I rerun this, that looks pretty awesome. It could be, I've seen plots like this. I saw one of these plots last time after class where somebody was showing me their convergence. And they said it looked kind of like this. And this actually looks rad. It almost looks like a fractal or something like that. And so it actually has something in common with that. So Brownian motion, it almost just looks like Brownian motion, and it's kind of walking around this space. Question is has this converged? And so I can kind of see that it's in some range, and it kind of stays in that range, and it's not drifting, but it's doing some other phenomena. When students show this to me, I say, you've got some notion of convergence, but I wouldn't trust any of this junk right here. And so we can kind of see that maybe our true answer is pretty far away. Mu maybe hasn't converged exactly yet. And so these are highly autocorrelated. So let's just write what this looks like. This is not a technical term. If anybody ever says this term and says, no, it's a used technical term, they've been hanging out with me for a long time. So this is called snaking. So that's snaking, not snacking. And this is also highly autocorrelated. So those samples are very correlated with themselves. And so the correlation is too high. It takes too long for the autocorrelation to wear off. And that will happen with both sticking and snaking chains. Both are bad. So let's just rerun this again and kind of play this game. So if it's snaking, I make the proposal variance higher. And if it's sticking, I make it lower. The difficult thing is when you have parts of your space that are heavily concentrated with low variability, and in another part of your space, you have high variability. And you kind of need to change the mechanism. None of the examples we'll be playing around with in this class are going to have that sort of phenomena. But again, that's what a whole MCMC class would be about, is showing you strategies to propose. The way I think about it, it's all up to your creativity. How do you get something to move around? And those are my favorite papers to write. So is MCMC papers, and figuring out what sort of proposal strategy would you use for some complicated problem. The fun thing is you can first write the applied paper with kind of a clunky sampler, and then you can go and fix your sampler and write a theoretical paper on the sampler. And then if you decide, because you're able to converge so fast that your model's wrong, you can change your model and play the game all over again and build a whole career out of this. I know people that have done that. I don't just mean me either. Like, that was kind of early 2000 Bayesians. That's what they did. So nowadays they're on to other things. Okay, so let's crank this up a little bit. Maybe make that 0.1 or something like that. Rerun. And that's starting to look pretty good. So it looks like it actually is converged. Keep in mind, we didn't grab any new data to do all of that. And so the name of the game is that you're able to explore your space, jump around your distribution quickly, move from the left and the right, you know, in the different tails of the distributions, move through it quickly and not jump too far out. And so there's this trade-off between moving too much and moving too little. You can decide if you like my analogy about life, that we're proposing utility, we're proposing something, checking our utility, and deciding if we want to go back there. And then we have to decide whether or not we're welcome back. So that's the analogy that I gave you. You can decide in your life, what do your proposals look like? Are you the type that tippy-toes around and says, I'm safe, I'm going to stay right here, so everything works for me? Or are you the type that is a constant adventurer and said, okay, I've done this for a while, I'm going to go see what it's like to go live in some far-off country? So that might be a little bit too extreme for some of us. But again, all exploration problems are the same. So this seems to have worked pretty well. So this, if you check the autocorrelation of these samples, it probably wouldn't be too high. And again, you might want to zoom in on this thing. So you might want to look at these samples and see what they look like. It looks like they're fuzzy all the way through. Don't see any strong patterns. I do kind of notice there's an up and down sort of thing. So it's snaking a little bit. So you can see some notion of it snaking. So you probably maybe want to crank things up just a little bit more. Now I don't want to teach you garbage rules of thumb. So there is a rule of thumb out there that says about 38% is your acceptance rate. And for a normal distribution using a normal random walk, that is optimal. So, but keep in mind, not everything's normal and not everybody's using that same proposal. And so that's in an idealistic setting where people can come up with a theoretical understanding of everything. But anyway, you don't want your acceptance rate to be 0.99. That's telling me you're tippy-toeing through your space. You don't want your acceptance rate to be 0.001. That's telling me you're sticking a lot. So, you know, 20 to 50% sounds like a reasonable range. Again, I don't put too much stock in this, you know, what the right rule of thumb is, because they're based off of usually trivial problems. So this thing does seem to have converged. So this is what I call a fuzzy caterpillar. So these things right here. Now that is definitely not a technical term. And if you hear anybody say that, they definitely have been hanging out with me. So, and I can tell you where the fuzzy caterpillars come from. So this, something that looks like that, so is what I call a fuzzy caterpillar. There's no, it's called caterpillar. Did I do it right? I think so. So I wrote a book a long time ago when I was in kindergarten called The Worms and the Caterpillars. If you ever want to know what the story is about, it's about people getting along. It's really what it's about. I got written up in the newspaper. I thought I was going to be an awesome author. The next year I wrote The Haunted Mansion and nobody cared. So there was a neat analogy in the story that I didn't even know I was writing about. But that's where the fuzzy caterpillars come from. So it's in this distribution, it's staying in this distribution. I don't mean to have it bending a little bit. That would be peculiar if you saw that. So this is supposed to be fairly static across. So it's come into the distribution and stayed in the distribution. So that's good. And I'll mention this has a low autocorrelation. sometimes in Bayesian papers that are using MCMC samplers to do all of their estimation, they'll usually say something like, I've run the algorithm for 10 billion iterations, and I've thinned for a bazillion iterations, and I checked my autocorrelation, and my autocorrelation was low. And they'll also do this one other thing that you'll sometimes see, and this is a variant to the Gelman-Rubin or the Geweke diagnostics. And in R, there is a package called Geweke, so that will run all of these diagnostics for you. But what they do is they break up everything into different bins. They'd probably make this a little bit longer, and they would bin it all up. And then they would compute the mean in each little thing, and they would ask, are the means the same in each bin? And they would do a test on that. But they wouldn't exactly test it. They wouldn't do the p-value thing. They would just end up looking at a test statistic. And they would look at something like the f-test. So for doing this. So this smacks of ANOVA. So analysis of variance. And in an ANOVA test, you're just checking if the means in different groups are the same. And the reason they don't do a strict test on it, well, one, it would be kind of weird to do like a classical test on these Bayesian samples, but these are not IID samples, right here. And nobody knows exactly how these are distributed because it changes with the problem at hand. So if you have a different target with different proposals, they might be distributed a little bit differently. So Gelman and Rubin and Geweke, Gelman, Rubin, Geweke, they all came up with a class of different test statistics, and if that test statistic is close to 1, then the variability in these groups is the same as the variability across the whole thing. That's where the terminology of ANOVA comes from. So they do an ANOVA type test, and they have a correction for the autocorrelation in there. And everybody writes down what the correction is, and then somebody writes another paper and says, my correction is better than your correction. And so this game continues forever. So, because there's no correct answer to it. If somebody really wants to know, you might say, I did the Gelman-Rubin Geweke test, so there's different variants of this, and I give credit to all 3 of them, and they have all authored together in some form or another. And so you end up saying that Gelman-Rubin-Geweke test statistic is close to 1, something like that. And that's all been programmed up in R, and there's packages in MATLAB that you can use to validate everything. I'm not going to ask you to do that for the homework, but if we were taking a full-blown MCMC class, we'd probably spend some time talking about all that. Instead, what I really do at first is I visually inspect my trace plots. So, and I'll even say that through visual inspection of trace plots, by looking at this sort of test score, looking at the autocorrelation, I've determined that the chain is converged. To end up combating somebody asking me the question about how do you know you didn't find a local mode, I end up saying something to the effect of I started at lots of different random starting locations and made sure it converged to the same thing. And so you never know for sure. And that's true in optimization as well. You never know if you found the absolute global maximum unless you know something about your target. So if you could end up saying it's unimodal and you've converged to something, then you could convince somebody that you've converged to the global max, the global min. So, same thing that any other field problems with. Any questions about all that? So we don't like that. You turn your proposal variance up. We don't like that. You turn your proposal variance, sorry, I said it the wrong way. You turn your proposal variance down, if you see that. You turn your proposal variance up if you see that. And if you see something like that, you're good. And if you have reviewers barking at you that they want you to be a little bit more formal than visual diagnostics, you can look up that, one of these. There's a lot of papers. And if you ever send me an email and say, what's your favorite current paper that you cite, I'll tell you what it is. So I usually just cite the old one. And I sometimes look at that. There's other things I do. You can read my own MCMC papers. All of these are proxies for convergence, so you never really know for sure. And I do have examples in my MCMC papers saying you can trick yourself into thinking you've converged when you really haven't. And so there's other things that you could do. Sam?
What type of trace plot would you expect if you had a distribution with multiple nodes?
You would see something like this. So, if you had a multimodal problem, and this is the clear example that you could think of, where it's like if you had something like this, there's some mode over there, and you've got some mode over here, right here, that are very far apart. Whatever proposal variance that you're using right here is not going to bridge you across that gap. And if you pick a proposal variance to jump you between these two things, they wouldn't explore very well. The other end of the string, so they wouldn't stay in here. So you probably need some sort of a mixture proposal. There's something called parallel tempering that's very popular to do. I'm not going to walk you through that, but that's kind of the obvious choice that a lot of people go running after. Personally, I don't love that algorithm. They're very hard to tune, but in simple cases, you can make it more. I've written a paper on that as well. So something called practical reversible jump in tempering. So there's something I've come up with called particle tempering. It's an MCMC variant that I think does work a lot better than parallel tempering. If you got this, what you would have is, if this was well tuned, you would have samples coming from this distribution, and then every once in a while you would jump over to this node, and you'd have samples in here. So typical algorithms for sampling from multimodal spaces, and I haven't given you the proposals to do this or what the process exactly looks like, but there is a Metropolis Hastings scheme, at least built off of the Metropolis Hastings scheme. It is Metropolis Hastings in disguise. Can come up with samples that jump around here for a while and then jump periodically. I'm not going to walk you through all of that unless you guys protest and say, I want 2 lectures on that, and I can give you 2 lectures on it. So we'll wait till the end of the class. So you guys have something you really want to see. But the typical sort of thing, so I'm going to say this is mode 1, and this is mode 2. And if you ran something and it converged to this, you might learn about what the shape of that mode is. If you ran another sampler and it converged to this, you might know what the shape of that mode is, but you would never be able to tell by running 2 independent chains how high that mode is compared to this. And that has to do with the frequency of how often it is in that mode. And that should be proportional to the area under that curve. You would see trace plots that probably look like this. It would convert, it would be in there for a while, and then bang, it'd be in here for a while. And then bang, it'd be in here for a while. And so if you ever see this, you know there's probably multiple modes going on. And a parallel tempering sampler or my particle tempering sampler would give trace plots that look like that. And so if you did the standard sort of Geweke thing, it probably wouldn't be the best thing to do, because you would end up checking for your convergence where the mean is over here. And while you could come up with a test statistic for that, and you could run it long enough that your test statistic would be about 1, the F ratio would be about 1, it's really a bad diagnostic to use, because it's very unstable in that part of the space. So I think for complicated problems, even though journal reviewers will accept this at a glance, it's probably not the best thing you can do. Make sense? Yeah, so when you see this, you get excited usually. It's like, oh, there's multiple nodes in my problem. This is fascinating. And so not just from an MCMC standpoint or statistical standpoint, but whatever's happening scientifically is probably really interesting. So every time I see multimodality, I'm always like excited. Oh, there's a mixture of things going on. It's not just one answer. There's multiple answers to this problem that are worth talking about. Personalized medicine, things like that. You know, different people respond differently to different treatments. We'll be touching mixture models soon, where we actually play around with these sort of distributions. And I'll be building up some MCMC philosophy for you there, too. Any other questions? Cool. So I think the best thing to do with MCMC is code up a whole bunch of them, run them, come up with different proposals. And if you do that long enough, you'll get really good at it. It's more about experience, actually doing it. It's at least my experience. Let me show you some theory as to why this actually works. See how far we get with this? Next time when we come in, we'll be talking about the Wishart distribution. Also, just a note, we will be doing a review session tomorrow. Be right back here. Note, review, tomorrow at 5:30 p.m. We'll also be doing one next week as well. Okay, this is called the detailed balance equation. So consider a Markov process. If you ever want to know what a process is, flipping a coin is a process. So it's a fancy word for doing something stochastic and repeating it over and over again. So stochastic processes is all about just repeating stochastic events. So this stochastic process is Markovian, and it only depends on the previous time step using our algorithmic time analogy. So consider a Markov process, and it's going to look something like this. I'm going to say P theta. So I'm going to use the notation that we're updating theta parameters just to kind of use our Bayesian analogy, that's what we're usually after is learning theta in our distributions. But this could be anything, any random variable. So this is going to be theta t plus 1, and it's going to be conditional on t minus 1. So that's my transition probability. If it were a discrete process, probability would be the right word. This is for discrete stuff. If it were continuous, we would use the word density. And if it was some mixture between the two, we couldn't use either one of those words. And so the word that we might use is rate. So if I didn't want to talk about probabilities or densities, then I might talk about rate. Oh, I know what Anna's bothered by. That would be a non-Markovian process. That'd be a two-step sort of thing instead of one-step thing. Was that it?
Yes.
Okay. So this is my Markov transition rate. Again, if that were a discrete thing, that would be a probability. You tell me the probability of moving from this state to that state. So be everything you need to do to write down a Markov transition matrix, and you can do it for every state combination. I'm going to imagine that this thing is continuous for our examples, but I'm going to use the word rate regularly. So this is the detailed balance equation. And I want you to remember this equation because this is the equation that you need to verify to show that your proposal scheme ends up giving samples from the target distribution, i.e. your Metropolis Hastings sampler works. So I'm going to call this the super equation. And I'm going to make it the super duper equation because it's so important to MCMC land. So this is the formula that we always need to verify. Nobody calls it the super duper equation, they call it the detailed balance equation. Okay, but it's that fundamentally important. So here's the equation. And again, this is really detailed balance. So if you say to somebody, the super duper equation, they are going to not know what you're talking about. Okay, but it is this important. So it looks like this. The transition probability, t plus 1. So that transition rate times this function right here. And I'll tell you what that function is in a second, is equal to this thing. This is going to be our transition rate, and this is going to be the backwards process. I need to spend a little bit of time talking about all of this right here. This is the backwards rate. So if I took my samples from my MCMC process, they'd be coming from this process. So my process is a Markov chain, and it has some transition rate. And we can compute that transition rate by accounting for the proposal step and the acceptance step. It's a hybrid between those two steps. And we'll encode what this means in terms of the Metropolis Hastings process soon. But this formula is always true in MC land. This is called a backwards transition. And so if you want to think about that, and this is the part that I'm going to sweep under the rug a little bit, because I'm not going to show you a lot of non-time reversible processes. But if I took all my samples from my MCMC chain after they burned in, and I looked at them backwards. So that would be the probability of moving backwards through that would represent those backward samples, the trajectory of those backward samples. Not all distributions are time reversible. So it turns out the one that I just showed you, at least for the block updated Metropolis Hastings, it is time reversible. And so in these things, when that process is equal to that process, i.e. the row is the same function, then we say the process is time reversible. I'm not going to write that down because this is the stuff I don't want to talk about. But if you want to think about non-time reversible processes, think about like melting a candle or something. Think about like an old candle that doesn't evaporate into the air, but it just melts all over the place. You could reasonably figure out what the blob is going to look like that candle melts into. But you could never figure out what the candle looked like. They created a blob. So I could say, oh, the blob will look something like this. It'll be in this area. It won't spill off the table, you know, because I know how much wax is there. But if somebody asked me, what did the candle look like? I couldn't tell you if the candle looked like a cylinder or if it looked like a dragon or something like that. It would still just be a blob on the table at the end of the day. So that's the heat equation, diffusion processes. Those are not time reversible processes. Very important in terms of numerical stability. The Metropolis Hastings process is time reversible. And so we can just keep that in mind. And we'll use that in our proof in a little bit. So if I take my samples and I look at them backwards, I shouldn't be able to tell the difference in everything. So if I have something that's heavily snaking around, that process should look about the same backwards and forward. So this is the stationary distribution. That's this pi right here. So this pi is exactly the same function when a Markov chain converges to its stationary distribution. That's the distribution that you'll wind up in if you walk through a Markov process. Now I'm kind of sweeping a couple other things under the rug. So aperiodicity, irreducibility, so the ergodic conditions. We'll talk about those later on. But basically my chain needs to be able to move from anywhere to anywhere eventually, not in the same time step. It needs to be able to come back to the same place that you started at. Can't just drift away from it. So that's called positive recurrence. And if you've ever taken a stochastics class, you'd be familiar with these terms. If you take an MCMC class, they'll definitely teach you all of this. And you also can't get trapped in some part of the space. So the whole space needs to be connected. Any Markov chain that has those properties, that you can move from anywhere to anywhere, come back to the original place eventually, and you don't do it in any funny systematic patterns. That's the aperiodicity condition, that you don't have patterns to things that start forming, that it's really a random process. The chain is considered ergodic, and all Markov chains that have that, bless you, have a stationary distribution. So that's always true. You might be familiar with something called a limiting distribution, that if I just run the process for a long time, it stays somewhere. So Markov chains that can move from anywhere to anywhere and come back with no funny patterns, their limiting distributions are stationary distributions. They're the same. That's about a month of a stochastic process class, is going through all of that. Saying that, if nobody told me any of that, I would believe this equation. I'd say, yeah, that's right. I wouldn't be thinking about this maybe as a stationary distribution in a temporal sort of process, or something that's moving iteratively. I'd just be thinking about this as a conditional probability, and I'd be thinking of that as the marginal distribution. And if the marginal distribution is the same at time step t+1 in t, and they're the same distributions, that's what we call stationary. If it's the same at step t and t+1, then it's the same at t+2 by induction. It's the same at t plus k by induction. So the process is the same regardless of the time point. That's the technical meaning of stationarity. The distribution converges and it doesn't move. So if I just thought about this as a probability thing and I didn't know anything about backwards transitions, I could accept this equation as being true. This is just a conditional probability rule. So this right here is the joint samples of being at theta t and theta t+1, and these are the joint samples of being at theta t+1 and t. So it's the same thing. So the super duper equation is an equation that you already know. And the only part we have to think about is stationarity, that this is a process. We probably need to spend a little bit of time talking about what backwards processes are. That is the part that I'm going to sweep under the rug. The important part is verifying the stationary distribution is the right target. And that's what we'll do next time. So what we're going to do is we're going to write down the Metropolis-Hastings process. This is what we'll do next time, and then we'll jump over to Wishart distributions, see how long we spend on this. But we're going to write down this equation, or this process. There's going to be two time steps, or two steps. This is going to be a proposal. It's going to come from some function. I'm going to use my Markovian proposal, t+1, theta t, and then I'll write down my acceptance rate. This is going to be the min of 1 pi theta star given x, pi theta t-1 given x. And then I would have to deal with my proposals. This would be g theta star given theta t-1. And then I would have the inverse of that in this ratio, theta star. So that's the Metropolis-Hastings process that we've been writing down. I update theta t accordingly. It's going to be either theta star, theta t-1. This is going to happen with probability alpha, and this will happen with probability 1 minus alpha. So what we're going to need to do to show that this actually converges to the target, so our target is our posterior distribution. This is the way the Bayesian uses this process. So we try to sample from our target. Our target is likelihood times prior, or posterior. So what we'll do next time is we'll write down what the transition rates are for forward and backwards time, and you'll have to just accept that backwards in time, it's the same thing. Just moving the algorithm backwards. We can use our imagination to prove that. And then what we'll show is that the target distribution is going to be that right there. So I've used pi for both of these, and that might be confusing. If you want to let this be a different letter, you could do that. So we're going to do two things. Write down our transition rate from this. What's the transition rate? Well, to move from theta t minus 1 or theta t to theta t minus 1, I have to propose something, and then I have to accept it. And so it's the product of those two things. And you'll notice this is continuous and discrete. So there's two things that go into that process. A continuous step, if theta lives in a continuum, and this discrete thing. So our word rate is really convenient. Because I don't talk about a probability, and I don't talk about a density, but I talk about the product of those two things. So we'll come back next time, write down what that process is, what these things are. This had a row in front of it before, and then we'll verify that this is the target that we want. I will be sampling from our posterior distribution. Okay, think about that for another few hours. I'll see you guys tomorrow if you have any questions at 5:30 with the homework and whatnot. And then we'll pick up on Wednesday. Thanks, you guys.